All right, in this video we're going to be looking at inverse functions. And inverse functions are real important in such things as solving equations. We've actually been using inverse functions for a long time, we just haven't called them inverse functions. Anytime you solve an equation, you're essentially using an inverse function. And we're going to need this as we move in to Chapter 4 after this lecture and begin to look at the exponential and logarithmic functions. We'll need to understand these ideas. So I first want to illustrate something with two different functions here. And in the last lesson we were talking about combinations and compositions of functions, and I'd like to find the composition of f with g in this case. So this will be a good review from what we did in the last lecture. So if you remember, f circle g, f composed with g, right? This is a new function, and how is it defined? It is defined as f of g of x. Notice again that we're composing, what we say composing functions. I'm plugging the output of one function, namely in this case g. I'm plugging in the output to the function g at x into the function f. So the inner function is g of g and the outer function is f. So what would this be in this case? Well, what is the function g of x? What is the output to the function g of x? If I plug in x, what's the output? It's this right here. 5x plus 4 all divided by 3. So now I want to take this as my input and plug it in to the function f. And what do I do when I'm evaluating f? Wherever I see an x, multiply it by 3, subtract 4 from that product, and then divide by 5. Last step. So I'm just going to replace the x in that formula there with this entire expression, so it's going to look a little crazy. I've got 3x is what? All this stuff. And then I have minus 4, and that's all divided by 5. And so, can I simplify this now? Well, yes. I notice right away when I multiply 3 times this fraction, 3 times 1/3 is 1, right? These cancel right here, and I'm simply left with 5x plus 4 minus 4 over 5. Well, now what? 4 and a negative 4 combined to 0. And finally, 5x divided by 5 is just x. And so interestingly enough, when I compose the function f with g of x, the output is just x. In other words, I get the identity function. Okay, I get the identity function. And what I would like, I did this example, I would like you to show that g circle f, remember the order we do the composition matters, right? This is g of f of x. I want you to show that that also is equal to x. It will look very similar to what we've done here, but I want you to show that that's also equal to x. And so when we have two functions that their compositions in both directions equal x, very important relationship, and I want to talk about that right now. It doesn't always happen, right, as we saw in the last lecture when we were talking about compositions, but in the case, if I have two functions where f circle g, or f of g of x, equals x, for every x in the domain of the function g, remember x has to be in the domain of g, and then g of f of x also equals x for every x now in the domain of f, right, which is our inner function now. In that case, as I've shown above, then g, the function g, is called the inverse of the function f. And we denote it this way, f with a superscript -1, which we read as f inverse. F inverse is called the inverse. And therefore, f of, well, we said g, but we're now calling f inverse. F of f inverse of x is x, and f inverse of f is x. And this little superscript -1, you want to be careful. This is not an exponent because f is not a variable, it's the name of a function. So this is not 1 over f. Okay, so you got to realize that f is not a variable, it's a function name. If it was x, you know, the variable x to the negative 1 power, yeah, that would be 1 divided by x. But this is just the name of the function, and the inverse in mathematics typically is indicated by a superscript negative 1. Okay, so first of all, I want to talk about, you know, how do we get to an inverse? What has to be true of the functions other than what we have here? Obviously, we have to have this relationship. So in order for this to work, we have to have a function that is what we call one-to-one. So a one-to-one function is a function such that no two distinct inputs have the same output. So distinct inputs give distinct outputs. All right. So that means, you know, notice for a function, right, we had what? For every input there was exactly one output. Okay. But it could be that two or more inputs have the same output. For example, think of the function f of x equals x squared. F of x equals x squared, just our good old quadratic function, right? The graph is a parabola opening upward. If I plug in, say, 2 into that function, 2 squared, I get 4. The output is 4. If I plug in negative 2, if I square negative 2, I also get 4. The output is also 4. So that doesn't violate it being a function, but it does violate it being one-to-one. So the function f of x equals x squared would not be one-to-one. Okay, so mathematically we can write one way is that if the two inputs are distinct, right, not equal to one another, then their outputs must be distinct, different from one another. That's the way we can write it. Graphically, we can use the horizontal line test. So if I were to look at this function over here, and clearly it's a function, some polynomial function it looks like, but for instance, at a particular height, a particular value of y, a particular output value here, if I draw a horizontal line at that height y, whatever that is, you'll see that I hit the graph in this case 1, 2, 3 times, right, as we see here. And that means what? That there are 1, 2, 3 different x values, right? These 3 different x values, these 3 different inputs give us the same output. And so the horizontal line test says if I draw any horizontal line and I hit the graph of the function more than once, then the graph, the function rather, is not one-to-one. Not one-to-one. So I'll abbreviate one-to-one with the 1-1 as I have here. Look at this function here. Can I draw any horizontal line and hit the graph more than once? As I begin to draw potential horizontal lines going across, it appears as though I only hit the graph exactly one time, not more than once. So the horizontal line test would indicate this is a one-to-one function. Going back to this function, looks like maybe some kind of a translation of the absolute value function, for instance. But clearly, if I draw a horizontal line, say right here, I'm going to hit the graph twice. And so again, we are not one-to-one. Okay. So remember, we had a vertical line test to determine if we have a function. Horizontal line test helps us determine if our function is one-to-one. So why is one-to-one good? Well, if a function is one-to-one, then it has an inverse. Okay. And so real important here, we can say this statement. If a function is one-to-one, and a little bit more exact, if the function f has a domain of A and a range of B, right, then its inverse, which we said it's going to exist, f inverse, has a domain of B and a range of A. Notice they swap, so the domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. And here's the definition. F inverse of y is equal to x if and only if f of x equals y. So let's see, why does this make sense, right? So if I plug x into the function f and output y, then the inverse function will take y as an input and get back to x, right? What we started with. Remember when we would compose the functions, we get the identity function? Yeah, so if I start with the function f, Plug in x, I get y out. I take that output, I plug it into the inverse function, right? And what comes out? X, what I started with. They cancel each other out. So this is important to understand this relationship here. Okay. And of course the reason why we need to be 1-to-1 for there to be an inverse, if I come back here and I look at this function, I would have trouble with the inverse function because I have 3 different inputs that go to the same output. Where would the inverse function send the output to? There's 3 different inputs. And remember, a function for every input can only have 1 output. So I don't know where to go back to. There's too many possible inputs to go back to. So I need to have it to be 1-to-1. So let's see if we understand this, right? If g of 3 is equal to 7, then g inverse of 7 is equal to what? Answer, 3. Right? And that's showing exactly what we talked about here for inverse functions. So if input 3 to the function, output 7, then 7 inputted the inverse function is going to bring us right back to 3. Essentially, inverse functions do what? They cancel each other out. They cancel each other out. By the way, if f has an inverse, right, and f is 1-to-1, has an inverse, f inverse, then the function f inverse also is 1-to-1, and it has an inverse, namely the function f. They come in pairs, they come together. They come together. And we're going to see this now. And what I want to look at now is how do we come up with a formula for the inverse function given a function that's 1-to-1? How do we find its inverse? Well, let's start with some simple ones here. And I'm going to use an informal approach, sort of an intuitive approach first to finding the inverse. So here's the function f of x, which is equal to x plus 5. So how do I undo this function? How do I get back to where I started from? This function does what? It takes the input and adds 5 to it. Well, I take the input and I add 5 to it. How am I going to get back to the original input then if I have added 5 to my input? The only way to get back is what? If I subtract 5. So the inverse function in this case is to subtract 5, right, from the input. So here, if I plug in 2 plus 5 is 7, right? So now when I plug 7 into the inverse, what do I have to do to get back to 2? I have to subtract the 5. 7 minus 5, I get back to 2. So they cancel each other out. And I mentioned, inverse functions are used to solve equations. You've been doing this all your life. If you're solving an equation and it says x plus 5, and it says x plus 5 equals 12, right? Then how do you solve this equation? How do you solve for x? Well, you say, I know, I subtract 5 from both sides, right? I subtract 5 from both sides, and I get x equals 12 minus 5, 7. Well, I'll submit to you that what you're really doing is just applying the inverse function. You're plugging both sides of this equation into the inverse function, right? So to undo adding 5, you subtract 5. And that's how these inverse functions work. Here's another easy one. F of x equals 7 times x. So how do I undo 7 times x? How do I undo multiplication? What am I going to do to get back to x if I multiply by 7? Somebody says divide by 7, right? X divided by 7. Or you can also think of it as multiplying by the reciprocal 1/7. Same thing. Okay. So those are some very simple and easy ones that we have. Let's look at a few more, get a little more involved here. What about the cubing function? How do I undo a cubing if I cube a number? So if I plug in 2 cubed is 8. If I plug in 4 cubed is 64. How do I undo that? How do I undo cubing a function? Well, answer, I take the cube root. The cube root of x, which by the way, can also be written as what? X to the 1/3 power. X to the 1/3 power. So there's the inverse function. Now, I'm going to use an intuitive approach on this one. You might say, well, that looks a little more complicated than the previous three, and you're right. But I'm going to find the inverse. And here's what we're going to do. So when you're evaluating the function f to begin with, let's just start there. If I'm evaluating, what do? I plug in x. What's my order of operations? What's the first thing I'm going to do? I've got to multiply by 4. It looks like I subtract 9. And then I've got what? All this, division by 11. Well, what goes first? Well, obviously I'm going to plug in x, and the first thing I'm going to do is I'm going to multiply by 4. Right? Essentially, I have a parentheses around this numerator. I've got to evaluate this numerator first, and then the last thing I'm going to do is what? Divide by 11, right? This horizontal bar means division. And so in the parentheses, right, I've got 4x minus 9. So 4 times x is the first thing I do, right? Do multiplication and division inside the parentheses before addition or subtraction. So I'm going to multiply first, and then I'm going to subtract the 9. So I'm going to multiply by 4 first, subtract 9 second, and divide by 11. Multiply by 4, subtract 9, divide by 11. So what I'm going to do for the inverse, to undo that process, I'm going to go in the reverse order doing the inverse operation. Okay, so let's see if this makes sense. So first multiply by 4, then subtract 9, then divide by 11. So to undo that, I want to go in the reverse order, which is I want to undo division by 11, which was the last thing I do here. The last thing I'm going to do in evaluating the function f is divide by 11. So the first thing I want to do here is to do the inverse of dividing by 11, which is what? Multiplying by 11. Right? And then what was the second thing I did here? Subtract 9. Okay. Well, I want to undo subtracting 9. How do I undo subtracting 9? I add 9. And then last but not least, the first thing I did here was multiply by 4. So now I want to undo multiplication by 4 by what? Taking this expression that I have so far and dividing it by 4. Right? And there's the inverse. Now, as you're finding inverse functions, it could be that we make a little mistake or something. Is there any way to check and confirm that we have correctly found the inverse function? Yeah. I want you to go back to our first problem in the video, which was what? Taking these two functions, right? Taking their composition and making sure that I indeed get x, right? In each case, right? And so you can do that. You can take this function f and compose it with f inverse and make sure that you indeed get x. And that will tell you that you have correctly identified the inverse. All right, let's take a look at number 5 here. Now, I want to take a look at the function f of x equals x squared. You might remember we talked about this one. This is an example of a function x squared, which domain generally is what? All real numbers. It is not one-to-one, right? And we talked about the fact if you square 2 or negative 2, you get the same output of 4. This function does not pass the horizontal line test, rather. Okay, but let's look at it now from this perspective. If I look at x squared for only values of x that are greater than or equal to 0, what's that going to look like? So we know 0 squared is 0, 1 squared, let's see, this is 5, 2.5, 2, 1. So 1 squared is 1, 2 squared is 4, it's almost 5. And 3 squared is 9. Here's 10, so just shy of that. So, right, now we know the parabola, if we graph the whole thing, right, what that's going to look like, right, the parabola opening upward. But we're only looking at values of x greater than or equal to 0. So I've restricted the domain, and when I do that, the resulting function I get is now one-to-one, right? Now any horizontal line I draw, I intersect the line of the function only once. So if a function is not one-to-one, we can restrict its domain to an interval such that it is one-to-one, and then we can define an inverse on that piece. And that's what we're going to do to the function x squared. Okay, so what's the inverse function? How do I undo squaring? How do I undo squaring? Well, I hope everyone says you take the square root. Okay, now, one thing that's important though, if you remember when we talked about the fact about the domains and ranges of a function that's inverse, Remember, the domain of the function has to be the same as the range of the inverse, and the range of the function has to be the same as the domain of the inverse. So when I look at this, let's see if that's true here. What's the domain of our function? Well, that's easy. We've said we restrict the domain to what? Only values that are greater than or equal to 0. Non-negative values, greater than or equal to 0. Well, is the domain of our function then the same as the range of our inverse? Well, let's think about range is the output. What do I get out of this? When I take the square root of any number, what do I always get? Square root of any number, I'm going to get a non-negative number. Square root of 0 is 0. Square root of 4 is 2. Right? Square root of any number, I'm going to get a positive or 0 output. I cannot get a negative number as an output. Right? There's no negative sign in front of here, so this is always positive. So yeah, the domain of our function is the range of our inverse function. Okay. What's the range of our function? What's the outputs? Right? Well, we can see it graphically are all the y values. What are all the y values? Well, I can get what? I go all the way down to what? The lowest y value is 0, right? I can't get a negative y value. There's no output down here. And the function continues to go up, right? That arrow means it continues on. There's no end to it, right? So the domain is again, the range is just like the domain. It's all values of y greater than 0, right? All values greater than or equal to 0, rather. Is that the same as the domain for our inverse function? Well, think about it. What's the domain? When I take the square root of x, x must be what? Greater than or equal to 0, right? X can't be negative, or we would be talking about an imaginary number, which we don't want. So yeah, the domain of our inverse function is the same as the range of our function. So there it is. I mean, I went through that very carefully, but you may be thinking, well, duh, we know that. But here I want to look at, what about if we look at the other branch of x squared, with a branch coming up here, right? That is this one, right, where x is now less than or equal to 0. If I look at the graph, in this case, if I square 0, I get 0. I square negative 1, I get positive 1. Square negative 2, I get positive 4. Square negative 3, I get positive 9. And we get this sort of branch, if you will, of our parabola. Okay. Well, what's our inverse function in this case? Well, how do I undo squaring? You say, well, I take the square root. But there's going to be a problem here, because notice our domain this time, right, up here was everything greater than or equal to 0. Now it's what? Everything less than or equal to 0. The domain of our function is all values of x, right, less than or equal to 0. Well, the domain of our function must be the range of our inverse function. But what's the range of this function? It's everything greater than or equal to 0. Right? So how can we deal with that? We can deal with that by multiplying by negative 1. Right? Now my range will be what? All values that are less than or equal to 0. Right? Now we match up. The domain of our function is the same as the range of our inverse function. And what's the range of our function? Again, the range are the y values. It's still everything greater than or equal to 0. Right? Still everything greater than or equal to 0. What's the domain of our inverse function? I'm still taking the square root of x, so x must be what? Greater than or equal to 0. So the range of our function is still the same as the domain of our inverse function. And so here's the difference. And so you see the difference depending on what branch you're on the function x squared. You've got two different inverse functions. Now, where does this come into play when you're solving an equation? Remember, when you're solving an equation like x squared equals 9, right, what would you say? You would say x is equal to what? Plus or minus the square root of 9, right? Which, of course, is plus or minus 3. And where does plus or minus come from? What are we talking about? Well, it's the negative and positive roots, right? And it's you're applying two different inverse functions, right? And that's what we have here. Okay. So when your function is not one-to-one, you're going to have two or more potential inverse functions to talk about. Okay. In the next video, then, I'm going to look at a more formal approach for finding an inverse. And in fact, we will come back to this problem right here, number 4, that we did intuitively, and I'll show you how to find it formally. And then we'll look at an inverse of a function that really you need this sort of formal approach. So that's what we'll look at in the next video.